Good afternoon to all. I'm Francesco Ancona from Polytechnic University of Bari, and I will present this work.
And I know they work also in the lock-in method for demographic analysis. With Professor Gallier.
Yeah. And I will present this work, study of the plastic behavior around the crack tip by means of thermometers. So, here we can see the outline of the works, an introduction and the aim of the work, a background about the thermoelastic stress analysis, some information about temperature signal and plastic behavior, then thermoelastic stress analysis for fatigue limit evaluation, for crack tip growth monitoring, and thermoelastic stress analysis used for the stress intensity vector calculation. Then our methods and data analysis, and then set up materials, and in the end the results of the work. So, classical method for monitoring the crack tip growth during fractal mechanics tests require the offline monitoring or also the online monitoring, but with the complex setup for the real and the evaluation of the crack tip position. So, the principal methods used for the monitoring are microscopy, ultrasound, X-ray, and other methods that we spoke before. And with thermal methods, such as thermoelastic stress analysis, we can evaluate also the crack tip position and the stress intensity vector with the same direct test with the infrared camera. The aim of the work is to propose, in this case, the innovative procedure to study the dynamic crack behavior of materials based on the analysis in time domain of the thermal signal. In this work, we propose this procedure to stainless steel, martensitic 1, and austenitic 1. So, thermoelastic stress analysis is a non-contact technique that provides stress maps of a component subjected to a dynamic load. The thermoelastic effect describes the variation in temperature, reversible, that occurs in a homogeneous isotropic solid when it's deforming in the elastic range. So we can relate the variation in temperature to the sum of the principal stresses through the K value, that is the thermoelastic constant of the material. A typical thermoelastic stress analysis setup provides a loading machine, an infrared camera, and a lock-in amplifier. The signal from the loading machine and the signal from the detector were analyzed by the lock-in amplifier, so we can have the outputs, the amplitude and the phase signal output. Usually the signal from the infrared camera, so the thermoelastic signal, is usually presented as a vector, where modulus is proportional to the change in temperature due to the effect. And the phase means the angular shift between the thermoelastic and the reference signal from the loading machine. So the infrared detector is able to detect the infrared flux emitted from the surface of the body. So we can relate also the principal stress of the surface of the specimen with the thermoelastic signal and through the calibration constant A. The calibration constant depends on material, equipment, sensor, setup, and the environmental condition during the test. The variation in temperature in the time domain can be written with this equation, known to all. These terms represent the main temperature variation. The second term, T1, the amplitude of the thermoelastic signal. This represents the phase thermoelastic signal, and then we can consider the other two parameters, T2, that is the amplitude of the temperature signal due to the plastic contribution at twice frequency of the loading machine. And the Phi2 is the phase of the temperature signal due to the plastic contribution. So we have to consider also not only the contribution of the elastic response, the variation temperature of the elastic response, but also the temperature due to the dissipation for the plastic work done in the application load. Thermoelastic stress analysis is possible to, we can monitor also the limit evaluation, fatigue limit evaluation, considering considering the temperature variation on the specimen. And our groups, in another approach, use the threshold method, an alternative method of the well-known Risitano method, to try to investigate the fatigue limit evaluation. And it's possible to investigate also the other parameters of the thermal signal to better understand the fatigue limit behavior. With the thermoelastic stress analysis, on the right we can see the classical phase image required during a fractal mechanic test. The phase value is normally constant unless the adiabatic condition are not achieved, like in the first region, so far from the crack tip region. Then, near the crack tip region, occur two phenomena that lead to a lack of the adiabatic condition: the heat generation due to the plastic work and the presence of high stress gradients. So there is a variation in phase signal from positive to negative. Then the phase signal value along the crack direction growth return to be from negative to positive, so we can estimate the position of the crack tip when the signal returns to positive value. Here are shown some results obtained for 30,000 cycles, 80,000 cycles, and 140,000 cycles for the evaluation, the monitoring of the crack tip position during the tests. With thermoelastic stress analysis, it's also possible to evaluate the stress intensity factor. So we can relate the thermoelastic signal through the stress intensity factor during the test. So, by simple consideration, considering an area around the crack tip position, we can evaluate trend of the maximum signal during the test. So, it's possible to evaluate the stress intensity factor only knowing the constant calibration of the test. It's possible to evaluate, for example, considering a dog bone specimen with fixed load, so we can, knowing the stress during the test, it's possible to evaluate the value of A. In this work, we used 3 CT specimens for each materials, martensitic and austenitic. The loading frequency was of 13 Hz, the load ratio of 0.1, and the specimens were sprayed with the fat black spray for increasing the emissivity of the surface. The loading machine was an MLTS with the load cell of 100 kN. The thermocamera was a FLIR SC6540. The data were processed by software IRTA, and a constant force amplitude procedure according to the standard. We made 3 acquisitions at 4,000, 48,000 and 112,000 cycle, and the pixel dimension was of 0.067 millimeters. In this, here we can see the result obtained, the image obtained for the 5 parameters considered. For the martensitic stainless steel at a stress intensity factor of 23.6, at number cycle of 48,000 cycle. From the first image, considering the mean temperature variation during the loading, it's not possible to evaluate the information about the crack tip position or about some information like the stress intensity factor and the other aspect that we have just speak about. So we have to consider also the other components of the thermoelastic, considering the variation of the temperature in time domain. So we can see here the results for the martensitic stainless steel. The first part, here we can see the trend of the CT2 component, so the amplitude of the second harmonic component, along the crack, the growth direction. So we can see two areas. A2 represents the plastic area due to the plastic work during the cycle. And A1 it's related to the phenomenon of the crack closure before the crack tip. And considering the phase of the second harmonic component, Phi2, it's possible to highlight a phase signal inversion in the same point where we is present the minimum between the two areas. Probably this phase signal inversion is related for the of the crack tip position. So we can see the same same result for the austenitic stainless steel, and the same consideration are possible to do the same consideration for the austenitic and the martensitic stainless steel. In this image, it's possible to see the comparison between the phase signal Phi1 related to the frequency of the loading machine and the two signal of the second component of the Fourier series. With this binarization of the image, it's with the same threshold value for all the image, it's possible to highlight the fact that with increasing cycles, the plastic area seems to be greater than the starts. And analyzing the T2 component, this is not the same thing with the Phi1 component. In the end, in this, we made a comparison between the phase signal Phi1 and the component T2 and Phi2. There is we investigate this behavior for the stainless steel, and we notice a difference between the evaluation of the crack tip position of about 0.2 millimeters, because for the considering Phi1, this point would be considered like the crack tip position, and instead with considering the T2 component, probably we have to consider the minimum value of the component. Here we can see the same behavior with a little difference between the position of the crack tip, also in considering the Phi2 component. We want to test other specimens to investigate this little difference, because we think probably it can depend on motion or for the resolution of the technique. So we have to improve this our resolution to have more information about it. In conclusion, it was proposed a new thermographic procedure for characterizing the thermal behavior of the crack growth in material. In particular, the amplitude and the phase of the thermal component and twice the frequency of the mechanical loading were studied by means of an analysis in the time domain of the temperature signal. Two stainless steel were tested, martensitic and austenitic one, and the constant force amplitude procedure was used on compact tensing specimen. The tests were made by using the infrared camera, and we put an extension ring in order to obtain higher resolution on the analyzed area. Information about the temperature variation due to the plastic behavior that occurs at twice the frequency of elastic deformation were obtained in this work, and the amplitude and the phase signal at twice the frequency loading seems to provide complementary information with respect to the thermoelastic stress analysis usually used for the characterization of the fatigue crack material. Thank you.